Okay, good morning, everyone. I'd like to welcome you to this Tuesday's Colloquium, and it's certainly my honor to introduce Patrick Chiang from Oregon State University. I've known Patrick for a number of years. He was an undergrad when I was starting grad school at Berkeley, so we overlapped a little bit there. He did his BS and UWEE at Berkeley, and then MS, PhD at Stanford University, and I think Mark Horowitz was your advisor?
Bill Daly.
Bill Daly was his advisor. And so it's an honor to have him here today. He's had a number of achievements. He's a tenured professor at Oregon State. He's won an NSF Career Award in 2012. And he's also won an Early Career Award in the Department of Energy, actually. And so his area of specialization is low power electronics and bioelectronics. So with that said, I will turn it over to Patrick.
Great. Thanks very much, Chris, for the introduction. It's my great pleasure to talk with you guys at UW today. Pacific Northwest has really nice weather these days, at the cost of California being a little bit hotter, of course. And the other thing that's great about the talk for me personally is my parents are UW alumni. Probably about 45 years ago, my dad got his PhD at UW in mathematics, trying to find the optimal convex portion of a derivative to find what would be the optimal. So it's pretty boring stuff. I shouldn't say that. Don't tell my dad that. Today I will talk to you about the research in my research group at Oregon State University, which is on energy efficiency at the extremes. And the initial title of this was this title, and then Chris said, you need to juice it up a little bit. That's not so sexy. So some portion of this I will actually talk about wearables, which will be the second half of this talk. But the first half I'll talk about actually cloud computing and exascale computing. So by the way, this is my research group, or was my research group. A lot of these guys did a lot of the initial work that we published together. And so this is the graduation picture that we had from last June. And this was the gift that they gave us, these T-shirts they made. So it says what people think we do, which is build rockets, think about ideas, and make microchips. And of course, the backside of the shirt says we only do Skype, Microsoft, and PowerPoint. so anyhow, so this is kind of obvious to many people, but the area of low power is critical for computing at both edges of the extremes that we see today. And when I say extremes, we look at two different portions. One is these massive scale data centers where we're sending all of our Fitbit data and our Apple Watch data, and we say, okay, it's gone somewhere, and then machine learning runs on it, and so what? It comes back to us, and we don't know where that data went. Actually, the data went to this guy here, which is a Microsoft data center in Washington. And you can see here that there are racks of computers, tens of thousands, and many, almost 100,000 to 1 million types of these interconnects between these different blade servers. Okay, so that's one aspect of where computing is going to when we talk about cloud computing. And just for your knowledge, 50% of all of the internet traffic today is going into the cloud, and in 2018 it'll be 80% of the internet traffic completely. Okay, so one aspect is how do we decrease the energy consumption in these large data centers? Of course, on the other end of the extreme is what are these things like cell phones or the next generation of Internet of Things? We're going to have billions of cell phones, which are essentially, we buy them yearly. But if Cisco's projections are correct of about 50 billion, internet-enabled devices, then what is the energy efficiency of these things, and how do we actually charge all of these devices if they're around us everywhere? Okay. More interestingly, or in future research, if we start looking at these wearable applications, everybody knows, the Microsoft M band actually works pretty well. Everybody knows the Apple Watch has some really great UI features. But one of the critical aspects of this thing is it only works for 18 hours. Okay, and so because battery density actually has not been improving at all, then all of the power consumption is in the microchips or in the display, right? So how do we make low power electronics that can extend the lifetime of these gadgets so that we're not charging them at all, assuming that battery technology is not improving, right? That's a big deal why these microchips must be low power. And then finally, if we're doing more than just wearing them, but we actually are inserting them in our bodies, Then we have these issues of deep brain stimulators, other types of very interesting electronics that are doing things in our bodies. But you can see here in this DBS stimulator, this entire wire electrode is a biphasic driver to that part of the brain. But this is actually done because you can't put a very large battery in your head. And so you actually would stick it in this location here and wire it out because you actually have the density to put it into your shoulder. So most of the cost, most of the implantation cost, most of the difficulty in the operation is really because of the battery. Okay. So from all of these aspects, you can tell that it seems today the most important thing now is the power consumed by these devices or the energy consumed by them, because it affects how much performance you have in a given device. Obviously, it affects its size and its cost. And finally, the reliability, because if we're going to trade off reliability with energy consumption, then we basically can actually tailor our precision versus the energy that we're consuming. So there's some other buzzwords here. This is one that Intel likes to use, which is not only talking about low power, but is there something called zero power computing, okay, which is, can we actually eliminate batteries? Of course, in a data center, that's not the case, but it is possible on the other extreme of things. So in my particular lab at Oregon State University, we focus on trying to build energy-efficient electronics in both of these extremes. And on the left extreme, we are mostly focusing on high-speed communications within a data center, or specifically optical transceivers. And this is some of the recent work that I did on my sabbatical in Shanghai, which is 25 gig or 100 gig transceivers, which are the receivers, clock and data recovery, and drivers for electrical optical conversion. And in my lab in Oregon State, we have been doing a lot of the most recent work on silicon photonics that you probably well know. Dr. Arca also works on the photonic ICs for this. We mostly focus on the electrical side of this, and I'll explain that in more detail in the next couple slides. On the right-hand side is the portion about the other extreme of low-power electronics, which is how do we build microsystems and ICs for these wearable applications, okay? And this type of design not only consists of the design of the IC itself, but we actually need to build applications that use these ICs and also integrate it into the software infrastructure. Because if we understand the software and the hardware co-design, then we can do optimizations between the two. So for example, we've done some stuff with compressed sensing where the cloud is actually providing feedback to the device, so the device is actually lowering its power based on some kind of adaptive, intelligent compressed sensing. And so this is more like a sort of a hardware software co-design. So we're building some embedded system designs using off-the-shelf components, but of course in the future we can do much better than just off-the-shelf by building our own specialized systems on chips, which might have, for example, microwatt or nanowatt level amplifiers, ADCs, milliwatt or less Bluetooth compatible radios, and then of course, like Professor Josh Smith works on, is basically wireless energy harvesting or other ubiquitous energy harvesting sources that limit the battery. So the outline for this particular talk today, first I'll describe to you the problem on the one extreme, which is how do we do exascale computing in large-scale data centers, and what does silicon photonics have in playing a role in reducing energy for these massive computers. And then on the other end of the extreme is, if we have these wearables everywhere, how do we reduce the power of these wearables as well as the radio? Because it turns out that the radio power almost 90% dominates the power of these wearables. And finally, if we have time, I'll show some more recent results that we've had on trying to eliminate the battery completely by using RF energy harvesting. So the first area that I'll talk about is the exascale data center application. So this came about approximately 7 years ago by the Department of Energy called the Exascale Initiative. And what it says is basically we have these massive high-performance computing machines in Los Alamos National Labs or the Cray Blue Waters at Illinois. And these kind of machines have these kind of characteristics. So in 2009, the IBM Rotor machine had 12,000 power PCs, 6,000 AMD GPUs, a cost of about $100 million, and a performance of about 1 petaflops in a power budget of about 2 megawatts of power. If you scale that up 3 more years by Cray, you can see the memory actually increased to about 1.5 bytes, and the cost probably remained about the same. The performance went up about 10x, but the power also went up about 5x. Okay, so you can see here that what's happening is that if we project this out to what the DOE wanted in 2018, they wanted another 10x in memory. Of course, the cost should stay about the same, but we need basically 1 exaflops of computation, which requires 100 times more performance in the same power budget. Okay, now that's an interesting proposition. If you think about that, it means that basically we need a 50 to 100x improvement in the number of operations per watt in terms of computational ability versus divided by the power consumption. Now note that in today's large-scale data centers, about approximately 1 watt of power is equal to $1 that you need to spend every year to power this thing. So not only do you worry about paying $100 million for the machine, but it's going to cost you, let's say, $2 million just to run that machine per year. Okay, so this is the focus of the first DOE Career Award, which is basically how do we build energy-efficient interconnect for this data center. Now, the question that you might have is why do we care about interconnect in a data center? Well, the real issue is most of your energy in a data center or a large-scale computer, actually even in a small scale like a wearable watch, is not in the energy consumed by the computation, but in the movement of the data. So this is an original study. It's a little bit outdated because it was built in 2008, 2009. But this is probably one of the most important things that you want to think about from this talk, okay, at a very high level, which is that essentially as we continue with Moore's law scaling, the size of the computational block is getting smaller because of transistor density is improving. So the energy it takes to compute on something is actually decreasing, but the amount of energy it takes to actually take that data and move it somewhere else, whether it's on the same chip between different cores on a die, or between that chip in DRAM, or that chip on this rack to this rack, or that rack all the way to the other side of the data center, that's consuming vastly more energy than the actual computation itself. And so here you can see a plot of doing a double position floating point operation, which is about 100 picojoules per operation. And then basically with Moore's law scaling to the transistor sizes, we're actually getting about a 5x reduction in the energy for that computation. However, the problem is that you can see here as we move that data farther and farther away from this computational point, we're consuming basically more and more energy, and it's not scaling with technology. And the reason is as follows. Moore's law is actually improving the transistor density per transistor, but actually it's making the wires closer together, right, because everything is getting closer. And so interconnect actually is not scaling that well with technology. It remains relatively constant. So if you think about like wire energy being on order of about CV squared, right, capacitance is maintaining about 100 femtojoules, femtofarads per 1 millimeter, and the supply voltage is not decreasing at all, okay? And so in this example, the on-chip energy is actually not improving that much. The same thing goes for off-chip energy as well, because if we have to drive an off-chip transmission line, which is 50 ohms, that impedance is not improving with more technology scaling. It remains roughly at 50 ohms, okay? And so that energy, again, doesn't improve with more transistors. So previously, we had done, maybe 3 or 4 years ago, we had done some on-chip interconnects, such as this network on a chip, where we have low power, low energy on-chip interconnect between different routers. So there's very low swing here, approximately 50 millivolts per on-chip link on a network on a chip. And you can also do very low voltage swing for the interconnect on die. And so we got about an 8x improvement on the energy efficiency versus conventional inverter-based interconnect scaling. In the last 3 or 2 years, we worked with Intel Research on using near threshold computing, which is to say we drop the supply voltage by 2x, but still maintain the same pin bandwidth by using parallelism here. So these are all operating about 0.65 volts, but with about less than 1 picojoule per bit of operation. So this is about a 4x reduction in the energy efficiency for off-chip links. But the problem that I'll show you, that I don't show you here, is we can't actually travel that far with these. These are very short interconnects between one chip and, let's say, your DRAM or your chip-to-chip interface, which has, let's say, about minus 10 dB of loss at Nyquist. The really tough problem is this farther out thing, which is we want a 20x reduction in the energy efficiency. We need long distance, though. We can't just go 3 inches. We want to go from this rack to another rack. So it's about 10 meters to 1 kilometer a data center. And these bandwidths are increasing enormously. Today, They want 100 gig of bandwidth in a form factor of a QSFP28 at about a 1 watt power budget, which is about 5 picojoules per bit. But they want 400 gig next year, and they want 1 terabit, let's say, 2 years from that. And so the only way you can do this really is if you move to the optical media, because if you stay in the electrical domain, basically you have a low-pass response, and you can't get the bandwidth you need. So we need to go to optics domain for that. Now the question is well, how many of these optical cables are in a data center or in a high-performance computer? It turns out there's quite a bit. So in the previous Roadrunner machine I showed you in 2008 had about 200,000 or 100,000 optical channels. This is probably an optimistic business slide from IBM, but it basically says in 2018 we could expect 100 million optical cables. I think that's completely out of the question, but on order of about 500,000 or a couple 100,000 optical cables in an interconnect in a high-performance computer is definitely possible. Okay. So the other thing you want to recognize is this is the DOE Exascale initiative. There are only 5 or 10, several of these high-performance computers. But actually, it turns out this is a big problem not only for high-performance computing, but also for these mega data centers. So this is an example in Quincy, Washington, of a Microsoft data center. It's basically 300 meters across, so almost 600 meters in total length, or about 1 kilometer, and it's about 2 football fields of data centers, of blade computing here. So you can see here is that basically all of these interconnects need to talk to the top of rack, and so you've got this rat's nest of optical cables, and also these very highly dense switches that are switching this internet traffic. So if you actually open up one of these cables, it looks like this kind of cable here. This fits into a slot here. It's about this big, a QSP28, and this goes for about $1,000 US, okay? And that's probably 10x larger than what Facebook wants today. They want about $1 per gig, okay? So Facebook wants us about $100 for 100 gig of bandwidth today, okay? Now, if you open up one of those widgets, then what you'll find is actually all of these chips inside are the ones that are doing all of the movement of data. So there are approximately 3 or 4 electrical chips. So electrical chip comes in, the data and clock gets recovered, and then it drives a optical driver, which is basically either a VCSEL driver or a modulator driver. That's electrical. It drives this photonic IC, which is doing the optical modulation. And there's also a receive path, which takes in 100 gig and then converts it to electrical here. There's basically an amplifier, then basically goes out this way. So all of these different chips have to burn on order about 1 watt together, including all of the optical electrical conversion and clock and data recovery. So these are all the chips that we've been doing in my particular lab inside. And the next question is why do we need silicon photonics, and what benefits does it bring? Okay? Because these are all conventional CMOS electrical chips, but they're going to be driving or working with this optical chip that is providing the conversion. So here's an example of a breakdown of a Google data center. And this is our fictitious example about what kind of distance these links are traversing versus what kind of technology you're going to be using. So for example, you've got a chip and this chip next to each other. If they're talking that close, you can just do 3D stacking. You will not need optical interconnects. So you can get away with half a meter to a meter's worth of electrical backplane or PCB trace. And then even if you have like a cable that goes up to, let's say, 2 meters or 5 meters up on a switch, you still can probably get away with electrical. But after about 5 or 10 meters, you're going to have to switch to an optical media, okay? And at that point, you need to decide, do you want to go to the traditional VCSEL approach, which is a multi-mode fiber wavelength, or to the more next generation, which is going to be single-mode fiber or a modulator itself. And so what's happening, it seems like today is, as an electrical guy, we've been able to push the data rates from 2.5 to 10 to 25, maybe even 50 gig electrical. But honestly, after 50 gig electrical per link, we have no solution. And I think you would be hard-pressed to find any company that in the world today that can say that we can do better than 50 gig in an energy-efficient format. And that's because we cannot solve the channel problem, okay? And because as we go to higher bandwidth, we get higher and higher loss, okay? So the only way that we as electrical know how to get higher than 50 gig, would be to go to multi-level, which is basically an ADC-based approach, or switch to an optical media. Okay, so this is kind of the issue: is can we use silicon photonics to move up this chain and sort of, as the bandwidths get higher and higher, eliminate electrical links from this proposition? Okay. So there are several optical types of devices that are possible to be used. Okay. The first is a VCSEL driver that we have here, and here you can see essentially a chip that we built that's driving a optical VCSEL. So light is actually shooting out of this vertically in 850 nanometers. This is a silicon photonic Mach-Zehnder driver, where we built this Mach-Zehnder driver driving a silicon photonic optical modulator. And this is basically a single mode driver. And then finally, the more holy grail solution is, can we use something like a ring resonator approach, which is much lower power than the Mach-Zehnder approach, and also gives us the ability to actually give us WDM. So what happens here on a very high level is each one of those circular ring resonators drops basically one wavelength at the circumference of the radius of that circle. And so if we can actually change the size of these rings, we can actually get WDM capability in a single photonic substrate. So each one of these things has a various bunch of trade-offs. And to my personal opinion, in the next 3 years, most of the things will actually be these VCSEL-based approaches. And the reason why is that VCSEL device basically acts as a laser source. Okay? These other devices, like this Mach-Zehnder one and even this ring resonator approaches, these are all your so-called silicon photonic designs, but they require a laser source to come into the optical device and get modulated out. And it's same as here. The optical light comes in this waveguide right here, and then basically this light is actually dropped off of that using this ring resonator source. So both of these solutions, even though silicon photonics is the holy grail, there's no way to make a laser source that is compatible with silicon today. And the problem here is that a laser actually has about, a VCSEL laser has about a 30–40% efficiency in terms of wall plug efficiency. A laser has about 5%. Okay? So if you want to actually go in terms of energy per bit, actually a VCSEL approach will be your best bet. Unfortunately, a VCSEL is a multi-mode fiber solution, and so cannot go farther than 50 meters. So for the rest of the data center, we have no choice but to go to these single-mode fiber approaches. So today, I'm not going to have time to talk about all these things, so I'm going to focus just on how do we build ring resonator-based devices which have this intrinsic ability of very low power, intrinsic WDM bandwidth. But their major problem is, you see that ring here, actually the phase of the light coming through to first order is going to be adjusted by the temperature coefficient. Because as the temperature is expanding, or temperature is heating, the ring is going to essentially expand, dropping the wrong wavelength. And so the biggest problem with this is not the power consumption, it's the reliability. Because with this because these things are so hot, we actually can't control which wavelength is being dropped. Okay? So how do we make this reliable is the next question that I'll show you next. Any questions? Yes?
Being dropped, what exactly do you mean?
Oh, okay. So in this particular manner, I need a physical pointer. So the light actually comes in through this waveguide, and it passes through on silicon using a silicon oxide, basically waveguide. And then this particular resonator actually couples that light and switches it over back into this other source. So we're only getting, basically it's an add-drop mux, basically. And so we're only getting the wavelength associated with that 10-micron diameter. Okay. If we wanted to get another wavelength, we basically build in, for example, a ring of 11 microns, for example, and we drop the proportion out that wavelength, respectively. So that's really nice because it actually gives us intrinsic add-drop mechanism and modulation with a very small 10-micron ring, which is very low power, basically. Okay. So the holy grail for this approach of silicon photonics is really a single substrate where the electronics and the photonics are integrated onto the same chip. And so you've got basically 4 to 100 different wavelengths of light, different lasers coming into a single waveguide on chip. And then basically we can couple light into that waveguide, or we can actually couple light out of that waveguide. So adding to that waveguide or dropping to that waveguide. So that gives us an infinite, quote unquote, infinite bandwidth per pin. because each pin now can have multiple wavelengths of light that's being added or dropped to that particular pin, okay, versus just a single channel. Now, you'll note, again, silicon photonics could in fact combine the electrical drivers and receivers and the photonic add and drop in the waveguide, but it doesn't seem like we can actually add this laser to that point, okay? And that actually seems to be the critical problem to silicon photonics today. Now, the way that this waveguide works, as mentioned before, is the light will actually pass through this waveguide, and essentially as we provide a reverse bias voltage and drive this ring at approximately several volts, we're actually going to couple light into that ring and destructively interfere with the light passing through, which gives us basically on-off keying for that particular ring. So you can see here, this is a measurement we made from, let's say, 1.3 volt drive versus 1.5 volt drive. You can see that we've actually switched the wavelength between which wavelength is being dropped by the driven voltage on that. Okay, so this is actually this is not a new technology. This has been done probably for the past 10 years. I think even like previously, Professor Hochberg at OPSIS was working on this kind of stuff 10 to 15 years ago as well. Okay, so the hard part about this is, well, it's got a really great ability to get you on-off contrast ratio, but again, if we have any thermal drift here, we're going to also drop the wrong wavelength as well. Okay, so analogous to this, total monolithic approach of combining electronics and the optics together, you could just split it into two different mechanisms. So in this example, we have a photonic chip in the center, which is optimized for the photonic process. And we have these electrical receivers and transmitters on top, which are optimized for the electrical process. This is probably what I believe is going to be the right solution. Okay? And the reason for this is we can optimize the photonic chip for the optic devices, and we can optimize electronic devices for the electrical properties, and we don't pay for the overhead for combining the two together. Okay? And then we use basically normal 3D stacking to achieve basically heterogeneous integration between these two. And this seems to be the approach that, in my personal opinion, may not be as energy efficient, but maybe more closer to commercialization because you can achieve low cost in this application where you separate the photonics from the electrical ICs. And so this is the paper that we published originally at ICC 2013. So this is an example of what we published in 2013. This is our first design, so we were not that smart about it yet. Here is a multi-channel 65 nanometer chip, and then we basically wire bond out to these really terrible long wire bonds to this photonic chip built by HP Labs. And here you can see the light is actually coupled into this waveguide here. It comes out of this one, and then basically this is the optical modulator here. So when we drive this modulator with about 2 volts peak-to-peak swing, we're actually getting on-off contrast ratio of the light passing through this optical waveguide. Now you'll note that this looks like a pretty, well, honestly, pretty crappy looking eye diagram. It's got a lot of noise on top and bottom, the 4-volt drive and about 5 gig of data rate. 2 years ago, this was reasonable, but it's still pretty poor. And there are a couple reasons for that. One is, as mentioned before, if we have any thermal drift in the heating around that ring, we're going to get deterioration of the dropping of that ring, which is going to give us noise on that. And secondly, it turns out that the biggest problem with photonics is actually not the electrical or the optical side, it's the actual alignment of the fiber to the actual input and output port of that optics. And that actually turns out to be most of your labor costs as well, doing the alignment. So what we decided was, most of the time you design for the worst case, we would like to propose, if you've got hundreds of these different channels, each channel is optimized for its own individual best case operation. So some channels might have more SNR. We lower the power based on that if they have more SNR. And if other channels are operating very poorly, we can increase the gain for those channels while increasing the power. So in this way, we're actually optimizing each channel for its optimal energy efficiency point. And this is another example where we can address that issue. Each channel has individual thermal and DC bias tuning, which is to say that we can measure the optical light coming out. If the light is poor, we basically retune the laser or retune the modulator to the right lasing point, and now we've actually locked the dropping point to the wavelength of the laser coming in. And you can do this using a thermal feedback loop, but in the example we've done here, we actually put in a voltage low-pass feedback loop, where we measure the optical output power passing through the modulator provide a feedback, and then basically are providing a low-pass feedback loop that's adjusting the voltage drive to basically precisely align the frequency with the right wavelength. So here you can see an example where we're providing a DC voltage here and sweeping the wavelength through to basically capture the right lasing wavelength. Not only do we do that, but we can also say that this particular design at 10 gig actually has an amplifier here and a feedback loop here, which is measuring the quality of your eye. And it says, hey, if we've got too much margin in our eye, why don't we just drop the gain? Okay? Because why do you need to operate at the worst case extreme when every link has a different type of performance? So in this example, we actually measure the quality of our SNR. And if we have enough SNR, we actually drop the SNR by dropping the front-end amplifier gain. So this is what these two feedback loops are doing. So for the same bit error rate of 10 to the minus 9, assuming that we can drop the input power almost by a factor of 2x if we have enough margin. Okay? So that's pretty nice, actually. So each link is operating at its own individual optimal point. So this is the design that we had from 2 years ago, but the most recent one that we published last month in ISSC is the next generation of that, which is can we get to this 100 gig multi-channel approach where we have our electrical IC here, which is then wire bonded to an optical IC here, and we have basically multiple wavelengths of light that are coming into this optical chip, and then each one is dropped through this optical resonator with an individual heater on it. Now, you'll note that this paper actually, again, was published in parallel with Professor Michael Hochberg's group. This is his photonic chip on the right-hand side at University of Delaware. And our IC is on the bottom here, which you can see here has very short wire bonds. So it's approximately 0.5 millimeter wire bonds up to each one of these rings here. Okay? And so this entire system we measured in the lab with not only are we doing this in 65 nanometer technology, we also have a thermal feedback loop here to compensate for any thermal drifts. So compared to the 2-year work before where we had injection mode modulator devices, this is a depletion mode device, can run up to 25 gig of data rate, but in order to get 25 gig, we need very large voltage swing. A conventional CMOS process only can do 1 volt swing. How do you get 4 volt swing that is still process compatible with an electrical process is actually pretty challenging. So we need large voltage swing and we need negative DC bias. So the way that we did this, I won't describe it to you today, but we have my PhD student was very smart, used an AC coupling approach here and voltage stacking to get basically twice VDD plus another 2x due to the AC coupling. The other problem that is very interesting moving forward in this area is electrical ICs themselves, we know almost everything we know how to do most of the things, but when we actually couple them to the optics domain, we find new challenges that we hadn't seen before. And this is one example of an interesting optical problem, which is the injection of carriers into the optical ring device actually has a faster transient speed than the removal of those carriers inside. So you can see here that the rise time and the fall time of the electrical chip actually, or of the optical chip actually has a different decay constant, and that's because of the nonlinear difference in the elimination of the carriers outside of that ring. So what we need to do as IC guys is understand this optical phenomena and actually provide nonlinear equalization to account for this nonlinear effect. And then finally, of course, as mentioned before, we have this problem of thermal stability, which is, yes, it's great if we can do this in a lab, but if the temperature is moving around, you can see that we're actually getting very closed eye just on very small amounts of thermal drift here. So what we need to do is build, as electrical guys, is measure this type of eye performance, feed it back, and lock the eye to achieve this kind of performance and not something on the extremities here. So we actually were able to do this, and this is what we published last month, which I think is actually pretty good work by my PhD student. So here you can see the optical eye here, where we don't actually apply the nonlinear equalization. So you can see here that really poor fall time is due to the removal of carriers from that ring. But because we know that that's going to happen, we can actually account for that in the electrical domain and actually get a pretty nice response. You can still see here there actually is still a poor ripple on the bottom side, but obviously much better than a conventional FIR filter would have performed. And then secondly, here you can see the optical performance at about a 2-volt swing is getting about 5 dB of extinction ratio with a 4.4 volt swing in a conventional 65 nanometer process. We're getting almost 7 dB of extinction ratio for this optical eye. So this is a pretty nice looking eye. Not only does that chip actually have the ability to do nonlinear equalization, but you actually have the ability to measure the output power coming through that particular ring, create a complete digital feedback loop here to compensate or basically measure that response and feed it back and adjust the on-chip thermal heating here, which is essentially heating up the ring to counteract any type of thermal drift here. So this entire ring here, when basically the thermal ring is not on, you can see the eye is pretty poor. After completely closing this loop, the eye actually is opened up to account for any thermal drift. Now, I still think we have a lot more work to be done here. You can see that this particular eye on the right here still has a lot more jitter when compared with this particular eye, right? And so the dynamics of how the thermal heating is affecting the photonic chip based on the particular enclosure is still unknown. I think we have a lot of interesting work to be done in that domain. But the point is that this is possibly be done. You can make ring photonics doable if we can provide really good thermal heating on a chip. So this is not only done for the transmit side. We also published a paper at ICC for the receive side as well, where we've got this silicon photonic chip. This chip is actually done by HP Labs, not Michael Hochberg's group, and then basically goes into the transimpedance amplifiers here, and then basically we gain out of our cells. So this also worked reasonably well. It's got about minus 10 dB of operation at approximately 10 to the minus 6, 10 to the minus 9 on order of about minus 9 dB. One thing you want to note is each one of those rings actually, even if they have the same size, and we believe that the same size, actually after process variation, we're actually getting different wavelengths. Okay, so that means that we not only have process variation in the transistors, but we have process variations in the rings themselves. And so we have to count for these rings and then basically calibrate them out. And so we can actually do that the receive side. Before tuning, we dropped the wrong wavelength. After tuning, we actually selected the right wavelength here. So I'm pretty optimistic on this work, and we're extending this further to 4-PAM modulation up to 56 gig and perhaps even further than that. Any questions on this?
That tuning is thermal?
This is a thermal tuning loop in this particular chip. And the problem with this particular chip is it's a depletion mode device. And so the voltage biasing mechanism for tuning is not as good. The injection mode device has a much better voltage to tuning range when you put a reverse DC bias on it. So what you normally like, so this is also interesting too, is you want to have maybe a coarse tuning using localized heating and a fine tuning per ring using some kind of DC tuning per loop. So you amortize the energy of the heating across multiple rings and then locally have a fine tuning adjustment. But for a depletion mode device, you don't have that much tuning range. And the other thing is, I think if you look at the numbers, I can't remember the exact numbers, the power, the amount of overhead and the power for tuning is not that high. It's about 5 milliwatts. And the receiver itself is like 30 milliwatts. So it's probably the thermal power consumed is about 20% overhead. Okay, so that's the conclusion of the optical portion of this talk. And now we'll probably talk about more fun things on the other extreme, which is wearables, and one aspect of the thing is how do we get to low power radios for these wearable applications. So if you look at the wearable market in general, it's pretty hot in US. Everybody talks about wearing these Fitbits and Apple Watches. And because I did my sabbatical in China, I saw that there was actually great need in these other areas as well. So here's an example of various types of FDA and non-FDA type of devices. So this is a device from Medtronic, or its a competitor. And this is basically the number of people who have diabetes type 2 is about 30 million people in the US. Interestingly enough, if you look at the Chinese, because of their increase in their middle class, They're also copying a lot of US things, including eating a lot of McDonald's and Kentucky Fried Chicken and a lot of soft drinks. They don't drink Diet Cokes that much. So here you can see that diabetes or pre-diabetes is actually a huge problem. I think on order of about 200 to 500 million people have pre-diabetes cases as well. Okay. In addition, if you look at heart disease, this is a product which is a 14-day ECG strip worn by iRhythm and Corventis. Basically, you would put this on your chest for about 14 days, and then basically it either Bluetooth wireless automatized to your cell phone, or you would just mail it back to them, and then they would download the data from the on-chip flash memory. There's about 0.7 million people in the US that have this kind of heart disease problem that can be a major problem. In China, it's almost 10 times that problem. But again, because they're eating too much McDonald's, then they have almost, in 10 to 15 years, 23 million people are going to have this heart disease problem. And so a company that I was actually talking with that wanted to get a design that we were doing, they were saying that they would try to pre-screen heart disease on order of about 100 million people to see if they had a problem. If they almost had a problem, then they would go to the hospital and then get the gold standard, which would be a normal Holter counter example. And then finally, obesity is a big problem in the US. It's about 35% of adults. And in China, even 30% of adults have this problem, but because their population is so huge, it's on order about 600 million people are pre-obese or getting to that way. So there's a lot of these kind of devices like Nike Fuel Band, Misfit Wearables, and these other devices. And so, inside one of these devices, interesting thing, that they look really nice. Apple Watch has a $10,000 gold-plated one, but the insides are the same. They're all microchips inside. And so what we decided to do was, well, if it's that easy, why don't we just build it ourselves? So we understand the problems, not only in the chip level, but also in the software interface as well. So we got a firm in Portland to design us the outside mechanical design. We designed the enclosure. And here you can see, actually, the interesting thing is this particular Bluetooth SoC plus the 3D accelerometer is only 2 chips. The BOM cost of this is probably on order of about $5. This Bluetooth radio right here is ridiculously complicated. It's got a 10-bit SAR ADC. It's got DC-DC conversion. It's got an ARM Cortex-M0 processor. And it's got a Bluetooth radio 4.0, which is burning about 8 milliamps in transmit and receive mode. Anybody have an idea how much that costs in volume? Let's say 100,000 units.
$1.
What's that?
$1.
$1. Yeah. Actually, you're too high. He was going to give us a discount for about 85 cents. Yeah. So unfortunately for the EE people in the room, which includes myself, we did a lot of engineering to get that cost down to 85 cents, which is phenomenal. But the other thing you want to note about that is, as these chips are getting so small and becoming quote unquote free, most of the mass and most of the size of your device actually is the battery here, right? This is a 2032 lithium coin cell battery. You can see here that it's taking up more than 50% of the size, area, and weight of this device. So I've got a whole bunch of toys here that we play with all the time that I'm going to just pass it around here. This is the device that so this is basically a Fitbit that we have here. It's already, of course, smaller. This is our first generation design that we did 4 years ago. It's got, at that time, they didn't have actually the processor and the Bluetooth radio together at that point. But now, essentially, we've got, this is only a 2-chip solution, and now we've integrated into essentially this kind of wearable device here. So I'm just going to pass these around here. So I'll give you first, I'll show you what was on these first before I get to that. Sorry about that. This is a Misfit Wearables device that costs about $99. It's nice because it's got aluminum anodized, but inside is basically the same thing. It's 2 pieces, an accelerometer and a Bluetooth radio. And this is, because I spent my sabbatical in China, this is a Shenzhen version. So it's exact copycat of this. It's got a BOM of about $9. It doesn't sell that well because it clearly doesn't have the same UI, right? And then this is the version that we built ourselves. So this is essentially our version of that type of Misfit. It's got a button push on it. And if you open it up, actually, you can see here, it's basically got 2 chips on it. Basically, that single chip Bluetooth radio with ARM Cortex-M0 processor and the accelerometer on that device. So now I'm going to pass it around. Yeah, it's fine, yeah. Don't want to lose the university iPad, right? So interesting enough, if you build all of these things, because we're hardware software guys, I actually have a bunch of students, including this really bright undergrad. He's only a sophomore, who actually, because we have the entire Bluetooth stack as well as the iOS software, he's holding in his hand basically that device, accelerometer device. So he's going to show you basically two apps here. One is the step counter app, and then one is, of course, the EKG app. So, this.
Okay. Hi, this is a demonstration of the WAM Wearables device platform. It's based on a Quintec ARM Bluetooth SoC, and I have a device here hooked up to a flexible heart rate patch and another device in my hand which is wirelessly sending Bluetooth data to an iOS device. So as you can see, the step count changes as I move the device, and it's live streaming my EKG data to the iPhone. Thank you very much for watching.
So this is not rocket science. Okay, we can build this platform, but the interesting question is, if we know how to build these devices by the way, I forgot to mention, this is a funded project by the USDA for about $5 million US, where we're actually doing a clinical trial of about 500 14 to 18-year-old kids playing soccer to try to basically use feedback from the iOS application and the device they're wearing to drop their obesity level. Okay, so we actually not only have to build our own custom ICs, but we also have to build the software infrastructure as well as the devices for these kids in this clinical trial. It's about 1,000 kids, 500 to 1,000 kids. Okay, so the interesting thing is, if we understand where this is going, then the question is as a EE guy, how do you provide value to this application? So if you look at what I've showed you here, we've got multiple chips inside our devices here. They've got basically maybe a radio, a CPU, an off-chip ADC, or different devices. The cost and the BOM is going to go up, and the size and power can be on order of about, let's say, 10 milliwatts at 3.3 volts. And so what we'd like to do is basically say, can we combine as many things as possible onto the same single chip substance? So in this example, we've got a system on chip that has everything that we would want. It's got the micro-powered analog to digital converter. It's got the Cortex-M0 processor, which we've already shown can be done. It even has a DSP and a compression block, and in the future, perhaps even localized security, because conventional public-private key security for Internet of Things really hasn't been done yet, right? And so a lot of people don't even want to use these devices because they're worried about their data being tracked. And so how would you do a very lightweight, low-power, low-cost security is an interesting question, actually. And finally, you want to put, of course, your wireless radio. It's got to be a very low-power read and write non-volatile memory, and it's got, of course, energy harvesting on that design to actually eliminate that battery. So if we can have a single chip and its cost is basically zero because the data is important and the cost per chip is going to fall down to 10 cents, but it can do all these things and it also has no battery, then this is kind of the holy grail of what we'd like to do. And so this is sort of the subject of the next project that we have, which is how do we make this type of chip be extremely low power? And the only way that we know, or the most efficient way we know how to make these chips low power is drop the supply voltage. And so this is kind of the area of near threshold computing, which is don't operate at the full supply, but operate as close to the point where the transistors are barely working, which is this near threshold operation. So previously, we had developed many types of near threshold chips for different portions of this system on chip. So here's an example of a most recent chip that we built. It's got a basically an amplifier for EKG, analog digital converter, which is about 16 bits, 10 microwatts power. It's got an ARM Cortex-M0 processor. Look how small that is. It's about 200 microns on a side, 4 kilobytes of memory on top and bottom. This is a really small MCU, right? That tells you you can do 32-bit processing with about 8 kilobytes of on-chip memory in a size that is basically nothing, right? And then finally, we've got, of course, on-chip compressed sensing. It's got this statistics collection module, and then, of course, packetization for sending to the radio, for example. So here's actually some interesting things I just got. I should have probably have filtered this a little bit. I just got this result about 2 hours ago from my really smart PhD student. But here's an example where if you just do blind compressive sensing on a time domain sparse signal, you'll get actually pretty poor reconstruction of the data. If you have a way to actually annotate your signal as it's coming through, of which portions actually has more information or less sparsity, you can actually aid your reconstruction and improve your SNR here. So here you can see, because we know when that peak is coming in, let's say we use our peak detection of the heart rate, we actually can provide more weight in the reconstruction, which will give us about a 10 to 15 dB improvement in the SNR by annotation. So it's basically sort of like, quote unquote, intelligent compressed sensing versus just, we blindly just compress it, the data coming through. And I think previously Professor Alstott was working on compressive sensing in this area as well. So not only do we need to have an SoC and the MCU for that, but we'd also like to have more sophisticated processing on the die, because if we just grab the data but don't process it and just send the data to the wireless link, then all of the power is going to be consumed in the wireless radio. So we'd like to do, various types of quote unquote parallel machine learning on the die, or some kind of signal processing to basically signal detect, sort of like peak detection or other kind of algorithms to minimize the amount of data transfer to the cloud. And so here's an example where we've actually dropped the supply voltage for 10 parallel lanes, and basically we're getting a 2 to 4x reduction in energy efficiency as we drop the supply voltage from high down to 0.53 volts. Now you'll note here, one interesting thing about this whole area of neurostructural computing is that the delay variation from 1 volt actually is pretty nice. But as we drop the supply voltage, you can imagine that the margin that we have to compute is actually getting worse. So the delay could expand from, let's say, 10% variation up to as much as, let's say, 2x variation delay. Okay, yes? Wrap it up. Time over yet?
Can you do it in like 2 or 3 minutes?
2 minutes, we'll finish it. Okay, so one interesting thing about this, and I think Professor Luis in CS was working on something like this, which is if the delay of your circuits are getting longer as we drop the supply voltage and more energy efficient, that means we have poorer reliability. So the question is, how do we operate on a parallel processor with unreliable outcomes, right? Because we can't expect the data to be valid or not, okay? And so there's some issues like probabilistic computing or something like, or stochastic computing. And it even gets to the point of we got the voltage down so low that we're expecting, if we're going to implant this in a human being, we're going to get actually cosmic radiation or neutrons that are basically going to give us soft errors that we cannot prevent. And so here's an example where we actually took our chips down to 0.3 volts and stuck them in a neutron beam in Los Alamos, and then measured how much effect the reliability would be as we drop the supply voltage down this low. Okay, so considering that I'm only partially done with this talk, I'll just wrap it up and say there are a lot of interesting things that we can do as we try to get to energy efficient computing. An example in the next portion would be, how would you build a radio at 0.6 volts that has basically a 5x reduction for a Bluetooth radio, or even Wi-Fi 802.11ah. How would you make it reliable? Because I know, as Professor Rudell does, it's very easy to build a low energy radio. It's very hard to build a backward compatible, robust to interference type of radio across this sort of ubiquitous area. So with that, I'm going to conclude today's talk. And if you have any other questions, please feel free to ask me any of them. Thank you so much. Yes?
Is your whole chip run at 0.6 volt, or there are some different voltage domains?
That's a good question. This particular chip now has 2 separate domains because the input amplifier has a lot of noise, because you want to actually minimize your noise. So we actually bootstrapped the first amplifier to 0.6 and double it to 1.2, but the rest of the chip is running at 0.6. But the current chip we're building now actually has the amplifier running at 0.6 as well. And we dropped that amplifier to, honestly, to about 1 nanowatt. This current amplifier is like 5 microwatts, and we've kind of built it to 1 nanowatt because the frequency is so low. Anybody else?
More questions? Yeah, go ahead.
I have a question.
Sure.
Could you talk about the leakage current affect your circuits?
Which circuits are we talking about? This particular chip?
Yeah.
This chip, oh, I'm sorry. Yeah, the question was, what about the leakage power consumption in the SoC? That turns out to be a really bad problem, as you mentioned. So for the amplifier, if you're operating at like 1 nanowatt of power, most of your power would be leakage. So we don't use the conventional thin gate transistor. We use the thick oxide device, which is a 2.5 volt thick oxide device. Its leakage current is pretty low. Okay. For the other devices like the processing and what have you, yes, they actually have quite a bit of leakage power. It's probably on order of about 30 to 40% for the dynamic switching power. But something for a radio doesn't matter because your radio power is just much higher than your leakage current. Yes?
I guess, I mean, so the processors are generally not as efficient as ASIC or even FPGA, right? If
What do you mean by
you
that?
design whole thing in ASIC, would it be more power? I mean, besides the radio part, would it be more efficient if you just process everything with the ASIC circuit?
This is an ASIC circuit.
Instead of ARM core, what's
Oh, are you saying don't put an ARM core and put something else inside? Oh, you're saying like a dedicated, yeah, I think that's a good question, but for a lot of these applications, we want to have some programmability, right? And that's why, in the future, you're going to need like a CPU, GPU perhaps, where you offload some parallel processing to the parallel core, but you have to have some general code. For example, like a lot of these wearables have like a big little core where you're offloading some sensor processing that is only a single MCU, but you might do parallel for your hardcore computing. But to answer your question, yes, dedicated ASIC will always do better than an MCU, but then programmability is your trade-off. Yeah, and both can be operating at near threshold.
I think Anthony had a question.
Yeah.
Real quick.
So I'm curious, with 1 nanowatt in the amplifier, what kind of noise floor targets do you have for EKG? Is it really, like, is it not very low amplitude signal?
That's a good question. So that's a good piece of research to do. It's basically how low power can you go while based on your noise sensitivity issue. Because as you drop the current, of course, your noise is going up. We're finding, at least in the lab today, or at least in our simulations, on over about 10 microvolts of RMS noise at about 1 nanoamp of current. It's like a 2-stage timer.
Okay.
Yeah, 2-stage. I'll have to get back to you on what the exact architecture, but I can. Yeah, it's on order of that. And that's a really good question: is how low power can you go while trying to minimize your noise? There are other ways, for example, looking at like noise canceling that you could try to attempt.
So one last quick question, Vamsi.
Yeah, so on this chip, you have an ARM core, but I'm just wondering, like, if you want to reprogram it, you need to have some non-volatile noise.
Yes.
And that's not going to work at 1 volt, or maybe, I don't know,
Good question. So you have a good PhD area to work on, if not another one. So in this particular one, we don't have a 0.6 volt non-volatile memory, and I don't think there is one that exists today, right? You could, for example, use the method proposed earlier where you bootstrap it up and then use that as your write power. And if you don't do it that often, then you could probably get away with it. But right now, today, I don't know of a very good way to do low voltage writing. Reading is probably okay. Yeah.
All right. I think we'll wrap it up there.
Great.
Thank you very much.
Thank you, Chris.